Okay, welcome to lecture here. We're going to get started. We're going to hopefully finish up chapter 7. We then should probably be rolling into chapter 9, actually, after that. Again, the notes are up online if you need them. Get everybody in here. Okay, so we've been talking about solutions last time. And a reminder again, a solution is made up really of two parts. One part is the solute, which is the smaller part of the solution. The larger part of the solution is known as the solvent. And when you put both of those things together, both the solute and the solvent, you get a solution. So, for example, if we take something like solid sodium chloride and we mix it together with water. They will mix together. The solid sodium chloride will dissolve in the water and it will make a solution. And again, the solute there would be the sodium chloride. The solvent would be the water in that case. Remember that basically the name of the solution is usually the solute. So again, if you have a sodium chloride solution, the sodium chloride is the solute. If you had a potassium chloride solution, the potassium chloride would be the solute. In a lot of cases, as we talked about, the solvent is water, but water does not always have to be the solvent. Water works really well, as I believe we also talked about, the idea of like dissolves like. So water, which is a polar molecule, works really well with polar solutes. They mix very well. And also ionic solutes as well, because they are able to interact really well with each other. So the idea of what we talked about in terms of sort of solubility and like dissolves like is the idea that things that share very similar sort of intermolecular forces, they're able to really interact over a long period of time with each other. So for example, if something can use sort of dipole-dipole interaction, and somebody else is using dipole-dipole interaction, it gives them a really good long-term way to interact with each other, and they typically will be soluble in each other. So things that are ionic and polar are very soluble in each other. Two polar guys are typically soluble in each other as well. Two nonpolar guys are also soluble in each other. Again, nonpolar and nonpolar, they'll be able to use sort of dispersion forces over that long period of time and be able to interact with each other through that way. It's only really, as we sort of talked about, when you sort of kind of cross over, if you take something that's polar and then something that's sort of nonpolar with it, again, for a short period of time, they have a way to really interact with each other. But as we talked about, I think last time as well, they really don't have any sort of long range way to maintain that interaction. So I guess maybe like the example, I maybe used the kind of oil and vinegar salad dressing. Again, for a short period of time, you could kind of get it to mix, but over the long haul, they really have no way to really keep that interaction happening because they're trying to use two different types of intermolecular forces. So what ends up happening is they sort of will separate out from each other and not really be soluble in each other. So when we cross over that non-polar polar things, they really don't mix. They're insoluble in each other. We also saw as well some solubility rules. Again, you can use solubility rules to determine whether or not, if you sort of put two ions together, for example, would you expect it to be soluble? And if it is soluble, that means that it would get the aqueous symbol next to it and basically make a solution. If it's insoluble, to get a solid symbol next to it and basically have some type of solid that's formed, a precipitate is sometimes called. We also talked about sort of concentration units that we use with solutions, and we saw a few different percent concentration units. 1% concentration unit was percent mass to mass, and that is the mass of the solute over the mass of the solution times 100%. The important part about that is the bottom part there. It is the mass of the solution. And I say that because usually in those type of problems, it's very common that they will give you the mass of the solute and the mass of the solvent separate from each other. So you typically have to kind of add those together to get the actual mass of the solution. Again, it's very common. People will just use the solvent on the bottom there instead of the actual total mass there of the solution. So you do want to kind of watch that for especially that percent mass to mass. That's usually the one that really does sort of come into play. We also saw percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. And that's basically milliliters over milliliters. So the volume of solute divided by the volume of solution times 100. And lastly, we saw the percent mass to volume, which is the mass of the solute over the volume of solution. So that again is kind of grams over milliliters, if you will, times 100 gives you that mass to volume. We saw that you could kind of plug it into the sort of formula for those guys. You could also kind of approach those problems as sort of conversion type problems, especially if you're given something like the mass percent or something like that. You could basically assume 100. So, you know, if I had a 0.45% sodium chloride solution by mass, that would mean I have 0.45 grams of sodium chloride and 100 grams of solution. So we can kind of use them as conversion factors. Lastly, we sort of finished up, I think, talking about molarity, which really is sort of the most common unit of concentration that we come across. Molarity is big M, and here that is. And it is moles per liter, and it is really the most common unit that's used a lot in chemistry. And you could kind of think of the formula as almost a formula, I guess, the molarity moles per liter. Again, it's very common that you have to kind of rearrange it like we talked about over here, and you want to solve for moles, and you need to take the liters times the molarity. Again, that is a very, very common calculation that is done using molarity. Also, this one down here, also very commonly done, sort of this rearrangement as well, that the liters, so sometimes you're just interested in, say, the volume that you may have, and that is equal to moles over the molarity. And lastly, obviously, just straight old solving for molarity, also a very common way. As we also talked about last time, molarity is sometimes just sort of abbreviated like this, 4.5 big M. And when you see that big M, it really does represent these two units, moles per liter. The number always stays with the moles part, and it's always 1 liter. So that's sort of how that sort of works. And you could kind of think of it like a conversion factor. You could flip it around like we talked about here as well and use the liters on top, the moles on the bottom. Now, when you do calculations that involve molarity, as I might have mentioned last time, I do highly recommend that you get rid of that big M and you do use it like we wrote it here, moles per liter. I can't tell you how many times people will leave the big M and have really no clue as to like where the liters are, where it is. Am I dividing by liters? Is the liter still there? You know, it's very common. People leave that big M and they really do sort of lose track of the units. So by switching it out to moles per liter, you could clearly see each of those units. You could clearly see if something canceled or didn't cancel. And I, again, would highly recommend not doing calculations where you keep the big M. Again, it is super, super common that people forget all about the liters part when they're doing these type of calculations. We also talked about sort of the relationship in terms of molarity and ions. When it does break apart, you could kind of look at the ions that are there and the molarity and think about it as sort of like a stoichiometry sort of situation. So I think this sort of example that we were talking about was if we knew the concentration of the whole thing, it's again a 1-to-1 relationship for the sodium, and it will end up with the same concentration for the sodium ions. It's also a 1-to-1 relationship between the whole thing and just the chloride ions. As you can see here, also ends up with the same concentration. So sometimes you're asked maybe not about the concentration of the entire ionic compound. You may be asked about the concentration of one ion versus another. And again, you can look at it based on how it breaks apart. If it broke apart into a 1-to-2 relationship, you would take the concentration and multiply it by 2. Any questions on any of that stuff that we talked about last time? Okay. Here's just a picture of those different types of units that we talked about here: molarity, mass percent, volume percent. So why don't we try one here, see if we remember. We're looking for what is the mass in grams of sodium nitrate that's required to make 2.5 liters of a 0.15 molar solution. Let me give you some numbers that you might need in case you don't have a periodic table near you. Sodium is 2299. Nitrogen is 1401. And oxygen, go here, is 16. All right, so take a couple minutes, see what you come up with. We're looking for how many grams of sodium nitrate there are in this solution that has that molarity and that volume. Okay, so I see some number coming in there on the chat. Let's take a look and see what we got going on here. So if you're not sure what's going on, we are definitely looking for grams here. We do have a volume that's given to us as 2.5 liters. We also have molarity given to us, which is 0.15 molar. So even if you weren't necessarily sure where to begin with this, you should think about molarity, which is moles per liter. And we do have the molarity given to us. We do have the volume given to us. So, it would probably be a good idea to figure out the moles. And that would be good because the moles here would be the liters times the molarity. And that's good because once we get the moles, we can use the molar mass there to go from moles to grams. So that's sort of the thought process here. Again, we're going to use this in sort of a calculation. This is the same thing as 0.15 moles per liter. And again, I would highly recommend kind of using both of those units so you can kind of see both units and see how they may cancel or not cancel. I'm going to approach this more like a conversion problem. So the moles will equal my liters, which is 2.5 liters. I'm going to times it by the molarity. Again, 0.15 moles per liter. Again, here the liters will cancel in this particular case. And if we multiply that, that will get us 2.5 times 0.15. Gets us something like 0.375 moles of sodium nitrate. Any questions up to that point? So at this point, we then need to really go from moles to grams. And remember that as we talked about earlier in a previous chapter, it really is the molar mass that allows us to do that. So that means we need to go to the periodic table. We need to take the formula for sodium nitrate, and we need to add up all the parts. So sodium is 2299 grams per mole. Nitrogen is 1401 grams per mole. And we have 3 oxygens, which each are 16 grams per mole. Again, all these numbers coming from the periodic table and the molar mass. And I want to say 85 on that, perhaps. Let's see here. Sounds good. And that would give us 85 grams per mole, which would be our molar mass for sodium nitrate. So really what is left at this point is really just a conversion. So we have moles. And we want to get rid of the moles and end up with grams. So here we're going to multiply by the molar mass. So 85 grams would go up on top. A mole would go on the bottom. And again, the moles here would cancel each other out. And looks like we will end up with 31.9. Looks good there in the chat box. 31.9 grams of sodium nitrate. Any questions on that calculation there? So basically what that number represents is if you scooped out 31.9 grams of sodium nitrate and you put it into like a beaker or a flask, whatever it may be, with some water, about 2.5 liters of water, you mixed it really well, all the solid would dissolve, and you would be left with a solution that has a molarity of 0.15. Any questions on any part of that calculation there? Okay, so again, a couple of things with molarity, like I mentioned, highly recommend convert it to moles per liter so you can see both those units. And again, think about sort of molarity equals moles over liters, sort of like a formula that you can rearrange to solve for liters, to solve for moles. Again, that's a very common sort of rearrangement of that that you have to do. All right, so let's take a look at each of these here. Give the concentration of the ions for each of these following that have this molarity. So I think we touched upon this last time, so let's just kind of go through this one together here. So looking at A first, the first thing we really want to look at is the actual formula here. So when we have something like sodium sulfate, it will break apart really into two ions. One ion is going to be the sodium ion, but we're not going to just get one of them. We will get two sodium ions. And again, that's what that two on the bottom means, that there's basically two sodium ions present. And we will get one sulfate ion that will be produced. So in this particular case, they gave us the molarity of the whole thing together, which is 1.2 molar sodium sulfate. And again here, since we're looking at just the sodium ion, for example, we want to kind of look at it really like a stoichiometry. For every one of the whole guys, we get two of the sodium ions. So it's basically twice as concentrated in terms of sodium ions. So how that affects the molarity is essentially we need to take the molarity and multiply it by 2, which means the molarity of the sodium ions in that solution would be 2.4 molar. And it's basically for every one of the whole units, you get two of the individual ions. So you get twice as much, twice as concentrated. And again, how that affects the actual molarity is you need to multiply it by 2. Now, when we look at the sulfate, for every one of the whole thing, we again get one of just the sulfate ion. So if we wanted the concentration of the sulfate ion, it would be 1 times 1.20 molar, which will still equal 1.20 molar sulfate. So really the simplest way to sort of figure it out in terms of the ions is just like that. Again, if it broke apart, say, into 1 to 3 relationship, you would multiply the concentration by 3. 1 to 2 relationship like we did, we would multiply it by 2. So same sort of approach that we would get here for our second guy, 0.75 molar K2CrO4. If we look at the K2CrO4, when it breaks apart, we will actually get 2 potassiums, again, what the little 2 means, and we will get 1 chromate ion, which is this guy. And again, you could apply the same sort of relationship for every one of the whole thing. We get, again, 2 of the potassium ions. So if we were interested in the concentration of just the potassium ions, we would need to multiply it by 2. So 2 times 0.75 molar would give us 1.5 molar potassium ions are present. And when we look at the chromate, it is a 1-to-1 relationship here. So again, 1 times 0.75 molar gives us 0.75 molar for the chromate ions. Obviously, when we look at the concentrations of the ions, they're not additive in that sense. Obviously, if you add 2.4 and 1.2, you don't get 1.2. But they're kind of proportion-wise, basically. When it goes into solution, you get twice as much sodium, for example, twice as much potassium. So in terms of their concentrations, it's twice as concentrated by doing that. And again, I think I worked it out last time, the actual long part of the calculation, but it's basically a mole-to-mole relationship. So I think we looked at it at that very front page. I had it, I think. Right here. So this is, for example, the long calculation of what we just did that we talked about last time. Again, using the formula as a conversion factor, for every 1 mole of sodium chloride, you get 1 mole of sodium ions. And you can see here, it's effectively taking 1 times it. Same thing with the chloride. So that's the sort of the long version of the calculation. How you go from the whole thing to the individual ion is really kind of that mole-to-mole relationship. And that is why when we get to what we just did, say here, we could say for every 1 mole of the whole thing gives us 2 moles of sodium. And that's essentially what this 2 is for. That's the big part of the long calculation. So that's just sort of the quick version of a way to do that without sort of doing the long calculation part. question on molarity, ions, concentrations, how that all works. Okay, so remember, if you have questions, feel free to ask them. So even if we passed it, we'll go back and make sure we answer them. So let's then talk about another aspect of concentrations, which is dilution. And in a dilution, essentially all we're usually doing is a lot of times adding more water or more solvent. So when we do a dilution of something, essentially we're just taking a little bit of the concentrated solution, adding more solvent. So again, a lot of times that is water, and we end up with a less concentrated solution when it's all said and done. And what happens is, as you can see on the bottom, the moles of the solute before the dilution is the same as after the dilution. Again, the only thing that you added is solvent. So how does that really work? So if you just think about molarity, which is technically moles of solute divided by liters of solution, when you add more solvent in this process, you're basically increasing this bottom number only, because the solution is both the solute and the solvent. So this bottom number gets larger, which means we take a small number divided by a large number, we end up seeing the molarity actually go down. So the molarity will decrease because of that. So we're essentially adding, again, more solvent, making the liters of solution a larger number, small number divided by large number, going to bring our concentration down. So sort of the same idea as perhaps maybe I mentioned before, you know, if you get a soda with a lot of ice in it and you let it kind of sit there for a while, it will start to obviously melt the ice. What that's going to do is essentially add a lot more water to your solution or your soda, for example. And it's obviously going to be a lot more diluted. It's not going to taste as strong as, say, it was when you first got it. And that's sort of the idea here. So there's different ways you could kind of make a solution or dilute a solution, but this is one way. This is what is known as a volumetric flask. And typically a volumetric flask means expensive, and that's because it has one marking on it, and that one marking represents the actual volume of the flask. So a lot of times you'll put a little bit of water in there before, you take your more concentrated solution and dump it in, and then pretty much fill the rest up with water to the line. And in this particular case, if this is 500 milliliters, that line would represent 500 milliliters exactly, total volume. And you give it a mix, you can see that our dark green, which is the more concentrated guy, ended up being a little bit lighter in terms of color. So it's a little bit more diluted in that sense. And again, what happens is the molarity of this guy ends up going down in the diluted solution, again, because you're adding more solvent and making that bottom number larger than the top number in that particular case. There is a formula that is used for dilutions, and this is sometimes referred to as the dilution formula. It is M1V1 equals N2V2, and it is pretty much what it kind of sounds like. M1V1 is the molarity, and V is the volume, and this is the molarity, and that is the volume. So this is like before and after the dilution. So usually this is the more concentrated guy. Doesn't always have to be, but usually this is the less concentrated guy when it's all said and done. And you could use this to figure out how to make a solution. M1V1 equals M2V2. Volume here, it doesn't matter. You could actually use milliliters here on both sides. It will work out perfectly fine for something we talked about, I think, last time as well. If you use milliliters, you'll just get milliliters on the other side, or if you use liters and use liters. But just to be clear, if you're using just the molarity formula by itself, the volume does need to be in liters. If you're using this dilution equation, the M1V1 equals M2V2, the volume here is okay for milliliters, but not okay here, again, because typically what you get, if you do use milliliters on the bottom one, that will actually get you millimoles and not milliliters. We'll actually talk a little bit about that when we get to acids and bases, I think. Um, so it will have a little bit of an effect on it because the concentration may change of your H plus, but we'll talk about if it will change that, I think, a little bit when we get there in the next chapter. Now, most people, when they do dilutions, will kind of use this formula, but I think your book may use it, and some other people books and stuff may use it, but they may use C1V1 equals C2V2, and this is really the same thing. The only difference here is C is concentration. So for the most part, like I said, molarity is the most common unit of concentration. But technically speaking, you could use this formula with any of those units of concentration that we talked about. So you could use something like percent mass in here on both sides, percent mass to volume. You could do percent volume to volume as well. You could use molarity. So sometimes people will kind of use this more generic version of the dilution equation. And again, you can use either one. I personally will use M1V1 equals M2V2, again, because usually you're dealing with molarity, but it doesn't have to be. So again, these are sort of two different versions of the same equation. So why don't you give it a try here and see what you come up with. What volume of 19 molar sodium hydroxide is needed to prepare 1 liter of 0.15 molar sodium hydroxide? To see what you come up with. So let's take a look at this. So we just kind of draw just so everybody understands hopefully what is going on here. So basically we have 19 molar sodium hydroxide and we want to make 0.15 molar sodium hydroxide. So first off, there is no reaction that's really happening here. We're just taking a solution that is more concentrated at the 19 molar and making it less concentrated at the 0.15. So you can kind of think of it as you got a bottle of 19 molar sitting over here, and you basically want to make a new solution that has a total volume of 1 liter and a new molarity of 0.15 molar. So this is definitely where we could use our dilution equation, M1V1 equals M2V2. And typically our ones are the more concentrated ones. So M1 would be 19 molar. M2 would be what we're trying to make, which would be 0.15 molar. V2 is 1 liter. So again, if you're not sure kind of where to start, we really don't know what V1 is. So that's a very good place to start. So we could rearrange this by dividing M1 to the other side. And that would get us V1 equals M2 V2 divided by M1. And in this case, as I mentioned, we'll put our numbers in 0.15 molar. Again, here we have it in liters. And we will divide by 19 molar. In this particular case, the molarity will cancel each other out. And this will give us a V1 of 0.0079 liters, or that is about 7.9 milliliters of the sodium hydroxide. So what does that number really mean? What that number really means, and typically speaking, when you solve for V1 here, that is usually how much of the more concentrated solution you need to take out. So what that means is we should go to our more concentrated bottle. We basically should take out and put in there, I'll just do it in milliliters, 7.9 milliliters of our sodium hydroxide. So the question is, what else should we put in there? The rest of what we should put in there in this particular case would be water. So you may ask yourself, how much water should I put in there? Well, 1 liter is the same as 1,000 milliliters. Would I dump in there 1,000 milliliters of water with my 7.9 milliliters of sodium hydroxide? And the answer is you should not, because if you dumped in there 1,000 milliliters of water plus your 7.9 milliliters of sodium hydroxide, that would give you a grand total of 1,007.9 milliliters, which is 1.008 liters, and that is too much volume. So you would not put 1,000 milliliters in. So you may be asked, how much water should I put in there? So typically to find the volume of water you need to add, you typically take V2 minus V1. V2 is your final volume. V1 is your kind of initial volume. And if you do that and you take 1,000 milliliters minus our 7.9 milliliters in this particular case, that will tell you you need about 992.1 milliliters of water would also need to be added. So we would put in there 992.1 milliliters of water with our 7.9 milliliters of sodium hydroxide. That gives us a grand total of 1 liter total. And again, at that point, if you did the old mixeroo there really good, that concentration of this new solution should be 0.15 molar. So it's very common in sort of dilution problems that sometimes they really want to know how much water necessarily, rather than maybe how much volume of something. So you want to make sure that you read those questions very carefully, because that's a very common sort of dilution question that's asked, like how you make it, how much water should you have added, and that type of stuff. Question on that. All right, so why don't you try another one here and see what you come up with. Um, how much water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from 5 molar solution? So see what you come up with. Take a couple minutes. Okay, so if we take sort of same idea here, we want to make a 0.25 molar solution of calcium nitrate from a 5 molar solution of calcium nitrate. Again, they're both calcium nitrate, no reaction happening or anything here. So we have a 5 molar solution that's more concentrated. So kind of the same idea. We have a bottle that is 5 molar. And we basically want to make a new solution that has a total volume of 500 milliliters and has a molarity of 0.25 molar. So again, when you're kind of thinking about this dilution, M1V1 equals M2V2, usually the higher number is your larger number. So we have 5 molar. Our M2 is 0.25 molar. Our V2 is 500 milliliters, and our V1 is we don't have. So again, that's a good place to start. Remember that typically when we're solving for V1, that again is how much of the more concentrated solution we need to take out. So V1 here would be M2, V2, M1. So putting in our numbers, 0.25 molar times our 500 milliliters divided by our 5 molar. Now, at this point, like I mentioned earlier, if you're using the dilution equation, it is perfectly okay to leave the milliliters. Again, when you solve for volume, you will be in milliliters. You also can convert it to liters. It's perfectly fine. The only difference is when you end up with your volume, you will be in liters. So again, here, if you're using the dilution equation, okay to leave our volume in milliliters. If you're, again, just using molarity all by itself, not a dilution, it needs to be in liters. Otherwise, you will get the wrong answer. So if you want to just be on the safe side on that, just convert it to liters no matter what, then you'll always be okay. But again, that's the reason. The reason why it's okay is right here, because the molarity and the molarity will cancel, and you'll be left with milliliters, basically. When you do that, you'll end up with something like 25 milliliters. Again here, that is not the answer. That is basically the volume of calcium nitrate that we need. So basically what that V1 represents is we should go to the more concentrated guy. We should dump in there 25 milliliters of it. So really the question, though, wanted to know how much water should we put in there with it. So the water really is usually the difference between our final volume and really our initial volume. So V1, V2 minus V1, and that would be 500 minus our 25, and that will give us something like 475 milliliters of water should be added. So when we add our 475 milliliters of water plus our 25, that gives us a grand total of 500 milliliters. Again, if we give a good mix, it should have a concentration of 0.25 molar for that particular solution. So again, this is a very common sort of dilution question where they ask more about how much water you need to add, how to actually make it, that type of stuff. So make sure that you do read these questions carefully. I can't tell you how many people will probably just circle 25 and call it a day at that point. And again, technically, that is the wrong answer for what they are asking. Any questions on dilutions or how to calculate dilutions? So again, V1 is typically how much of the stronger solution you're taking. V2 is your final volume. Usually M2 is your final molarity of your diluted solution. And typically M1 is the more concentrated concentration there. Any questions on any of that there? Okay, so we will then talk about properties of solutions next. And some of the different sort of properties that we have. One thing is known as a semi-permeable membrane, and it's basically a membrane that separates really two sides. And it basically will allow certain size molecules or particles to pass through and others not so much. So although usually you can't necessarily see it, a membrane, essentially has, all, for lack of a better description, holes in it. And these holes basically are of a certain size, which allows certain things to be able to kind of pass through it. Other things that are maybe way too big are not able to get through the hole and are basically trapped on the other side. Our cell has membranes that allow, again, certain things to kind of pass through and other things basically not to pass through. We also have things that are known as colloids. Colloids are really larger than solute molecules or particles. These are large particles, are molecules like proteins and groups of molecules or ions that are together. They are homogeneous colloids. Homogeneous, if you remember, basically means that it kind of like a solution looks the same throughout. They typically do not separate or settle out. They are small enough to pass through filters like a filter paper, so like a funnel that has like a filter paper on it. So colloids can pass through. But they are too large to get through sort of the membrane. So colloids here, again, would get kind of trapped here based on its size. Suspensions, on the other hand, suspensions are heterogeneous mixtures. Heterogeneous, if you remember, basically when you see kind of different layers, and they're very different than solution or colloids. They are large enough that you could kind of see them with your naked eye, and they do get trapped on both filters and membranes. So they're too big basically to go through either of those things. So for example, here's sort of an idea here. We have solution, which are their circles. They are floating around. They really don't settle out. Neither does the little triangles, which are colloids, but suspensions do, right? So a lot of medications come as suspensions, right? There you could definitely see things on the bottom, and you got to kind of give it a good mix, right, before you kind of use it. So you can see that suspensions really do kind of settle out. Here's our filter paper. Again, you can see going through both our solution and also our colloids, but again, our suspensions getting caught up there on the filter paper and not passing through. And this sort of like dialysis site bag, which is a membrane, again, you can't necessarily see the circles on it or holes, but again, allowing certain size particles really to pass through, other size not so much. And you can see that the solution is able to sort of pass back and forth out of the membrane with no problem. So that brings us to an idea which is known as osmosis. And osmosis is when we do have sort of solvent molecules basically moving from one side to the next. So a lot of times perhaps you have, say, a solution and say a tube or something like that. And you have sort of a membrane in the middle. And on one side, say you have salt water. On the other side, say you just have regular water. And by osmosis, what's going to happen is the water, which is less concentrated, is going to move from the water side to the saltwater side. And it will flood into sort of the saltwater side of the tube in an effort really to try to really dilute it down. And it will continue to flow into the other side until it reaches something which is known as osmotic pressure. And the osmotic pressure is basically the atmospheric pressure pushing back down on it. And when it does and it reaches that osmotic pressure, it will stop the flow basically of water molecules from one side to the next. So the natural process of osmosis is we have things that will flow from a lower concentration to a higher concentration in the effort of sort of diluting it down. What creates basically a sort of osmotic pressure, it has to do with the number of particles that are dissolved in the solution. The more particles you have dissolved in the solution, the greater sort of the osmotic pressure. And that is why pure water, which is H2O, that has nothing dissolved in it, will have an osmotic pressure of basically 0 because there's nothing really dissolved in it. One way sometimes that we represent osmotic pressure is what's known as the osmolarity of a solution, sometimes referred to as osmol. And that is basically I times the molarity. And what is I? I is the number of particles in that solution. So for example, if you have water, it's not going to break apart into any ions or anything like that. I would equal 1. Now, if you took something like, say, sodium chloride solution, when that breaks apart, you get a sodium ion and a chloride ion basically flying around, which means that I, in the case of sodium chloride, would equal 2 ions you get for every one of those. So let's just say, for example, we had a 0.25 molar sodium chloride solution and a 0.25 molar calcium chloride solution. Which one would have the greater osmolarity? Well, sodium chloride's osmolarity would be 1 times 0.25 molar, which gives you 0.25 osmolarity. But when something like calcium chloride breaks apart, it breaks apart into a calcium ion and 2 chloride ions. That's a grand total of 3 ions on the product side. And that would mean I would equal 3. So if we did the same calculation for our calcium chloride, we would take 3 times 0.25 molar. And that would get us 0.25 times 3, 0.75 osmolarity. And that would be much higher in terms of the osmotic pressure, again, because it has a lot more particles dissolved in the solution. So the greater amount of particles usually dissolved in solution, the greater the osmotic pressure, and the lower the osmotic pressure. And again, water really doesn't have anything dissolved in it, so it really has 0 in terms of the osmotic pressure. Now, here's a much prettier picture of what I drew, but same idea here. Again, we're going to have that flow of guys in until that osmotic pressure, which is basically, the atmospheric pressure pushing down on it to stop that flow of solvent molecules from one side to the next. So something like sodium chloride, when it's in solution, it doesn't stay together. It breaks apart into sodium ions and chloride ions, which means for every one of the sodium chloride, you actually will get 2 particles in that solution, 2 ions. And what that means is I would equal 2 in that case. It would give you 2 particles in that case. Water doesn't have anything dissolved in it, so it basically has no particles floating around in it. Just like if we had calcium chloride, when it breaks apart, you get a calcium ion and 2 chloride ions. That's a grand total of 3 particles per solution. So the number of particles you have in solution will affect something like the osmotic pressure. The more particles, the more osmotic pressure that you would have. Water basically is 0. Again, it has really no solute dissolved in it. Water is basically just a pure solvent. It has nothing really dissolved in it. And that's why pure water, H2O, has an osmotic pressure basically of 0, because it has really nothing floating around in it. Remember when we say aqueous here, there's water involved here, but in that water, in the case of sodium chloride, we have 2 ions floating around. In the case of the water with calcium chloride, we have 3 ions floating around, creating greater osmotic pressure. So as I was talking about, when that water molecule flows to the other side and it's basically stopped by that osmotic pressure, that's basically what reverse osmosis is. Reverse osmosis, you apply a pressure greater than the osmotic pressure heading in this direction. And what that will essentially do is force all that water molecules back to the other side. And if you have some really good filters happening right there, you basically can catch all the contaminants, and you'll actually end up with, kind of really pure water and stuff like that. So that's sort of the idea behind reverse osmosis. You put down a pressure greater than atmospheric pressure, basically pushes all that kind of water by itself back the other way. You have a lot of filters that will grab everything else. And that's, again, a kind of a way to sort of purify, for example, water and stuff like that. Any questions on that there? There's also another way that we sometimes describe solutions, and we describe solutions as what we see on this slide here as being isotonic, hypotonic, or hypertonic. When we talk about an isotonic solution, that is something that has the same osmotic pressure as body fluids. That is typically what IV solutions are. And there actually is 2 solutions that we typically consider isotonic. Usually 0.9% sodium chloride, or sometimes called a saline solution. It doesn't necessarily have to be sodium chloride. It can be like potassium chloride, something like that. And a 5% glucose solution, And these are usually like mass to volume percent. Glucose solutions. So these guys are considered isotonic solutions, which means the nice thing about isotonic solutions is, for example, if you have like a red blood cell, for example, and you put it in an isotonic solution, water will flow in and out of the cell pretty much equal to each other, which is probably a good thing, I'm imagining, for your cell. That is also why they give people isotonic solutions as IV solutions, because if you're probably getting an IV, you're probably not in the best shape. So they don't want to give you something that's going to kind of screw up your cells, right? So it wants to make sure that your cells are okay, and it needs to have really the same osmotic pressure as body fluids, and those isotonic solutions allow to do that. But now if you take something that is a hypotonic solution, hypo means less than, so it would have less osmotic pressure outside the cell, for example, than inside the cell. And if we just think about that, so if we took that same red blood cell and we put it in a hypotonic solution, again, outside is less concentrated than inside. What's going to happen is osmosis is going to make all the water, the solution outside of the cell, start to float into the cell. A cell is really like a membrane, basically, right? So all the water will flush into the cell. That's going to cause that cell to start to swell and possibly burst, which I'm assuming is not a good thing. And that's going to cause hemolysis. And again, not a very good thing happening in that case. So again, hypo meaning less than, by osmosis, water going to flow into the cell, causing it to swell and burst. We also have a hypertonic solution. Hypertonic solution means greater than. That means that the solution outside of a cell, for example, is greater osmotic pressure than inside the cell. So again, if we take our poor red blood cell here and we put it in a hypertonic solution, that means that outside of the cell is more concentrated than inside the cell. So your cell's going to go, I need to do osmosis and I need to dilute this water and stuff, or what, not the water, but the solution outside of the cell. And what that's going to happen is all of the sort of water or a part of the cell is going to flow out of the cell. And that's going to cause the cell to start to shrink and cause crenation, which is not good either. That's obviously not going to be a good thing. So how do we know, what's going to happen in this situation? Again, you want to remember these two numbers here. These are the numbers that help us determine whether or not something is isotonic or hypotonic or hypertonic. So for example here, let's say we take a red blood cell and we put it in, we'll go with a 5% sodium chloride solution. And let's say we put it in a, let's go with, a 2% glucose solution. Let's go with a 0.9% sodium chloride solution. And let's go with good old pure water. So what I want you to determine is what's going to happen to the red blood cell in each of these cases. Will it be okay? Will it shrink? Will it swell? So take a couple of minutes here and think about, if you put a red blood cell into each of these solutions, what you would expect to happen. Okay, so let's sort of think about what's going on in each of these solutions. So a couple of things that will help us again is these numbers here. So these numbers here are isotonic. So we know that if it's, something like a red blood cell is put into those solutions, we would expect nothing really bad to happen. And again, we really want to use these numbers as sort of our, is it that number, which would make it isotonic. If it's not that number, then it's either higher, which would be hyper, or lower, which would be hypo. And in certain cases, again, if it swells, that's hemolysis, right? And then if it shrinks, that's crenation. So let's take a look at the first one. First one is 5% sodium chloride. So remember that it is 0.9% sodium chloride is isotonic. So really it's just a number. So 5 is greater than 0.9, which means really this guy is a hypertonic solution. And that means, again, if we put our red blood cell into that solution, outside of the solution is more concentrated than inside the solution. So all of our water from our cell is going to rush out of the solution in order to try to dilute it. And that is going to cause the red blood cell to shrink and go through crenation in that particular case. Question on that particular one. Looking at our next one, which is 2% glucose. So glucose is important here. Remember that a 5% glucose is isotonic. So 2% would be less than 5%. And less than means that we are now dealing with a hypotonic solution. And that means that when we put our red blood cell into a hypotonic solution, outside of the cell is less concentrated than inside the cell. That means everybody's going to rush into the cell, and that's going to cause the cell to start to swell and go through hemolysis and burst, and not a good thing. Coming here to 0.9% sodium chloride, 0.9% is an isotonic solution. So that is an isotonic solution. That means if we put our red blood cell into our isotonic solution, water would go in, water would go out at the same rate, and your cell would be okay in this particular case. Nothing bad would happen. Now, if we come over here to pure water, you may say to yourself, it's water, it can't be bad for you. In this case, it actually is bad for you. Water is 0 osmotic pressure, which means it is actually hypotonic in this case. It has nothing dissolved in it, it has no osmotic pressure, which means if you put that red blood cell into the water, it's going to be hypotonic, and actually the water will rush into the cell, causing it to start to swell again and burst. Any questions on that there? So if you had 1% sodium chloride, 1% is technically above 0.9, and that would make it hypertonic. And again, in that case, it would be similar to what we had going on here in terms of the red blood cell. So the water would rush out of it and try to dilute the outside. And again, it would cause it to start to shrink and go through crenation. Yeah. So those two numbers are sort of important cutoffs. And again, like I said, although most people will do the 0.9 sodium chloride, again, they sometimes will call it a saline solution. It's sort of a 0.9 ionic sort of compound. Usually is sodium chloride, but again, it could, like I said, could be something like potassium chloride or something of that nature as well. So, but usually sodium chloride or saline is the common sort of phrase for that. Other questions on hypotonic, hypertonic, isotonic solutions? Here's just a picture of them, probably better than what I drew. Yes, so if it's higher than 5% glucose, it would be hypertonic as well. So those are really your two cutoff numbers in most cases. that 0.9% sodium chloride, and that 5% glucose. And again, really, it's as simple as looking at this number and going, is the number I'm looking at higher or lower? If it's higher, it's hyper. If it's lower, it's hypo. Or if it is that number, it's isotonic. And same thing with the 0.9. Again, you kind of want to use that as your kind of, this is isotonic, and then either it's higher or lower than sort of that number to decide what type of solution you would have. In the case of isotonic here, you're welcome. We have our red blood cell. It kind of looks like a happy donut, water going in and out. Here is our hypotonic solution, water flowing in. We have our jelly donut as it starts to burst. And our hypertonic solution, everybody going out of the cell of the solution, your donut hole, just in case you want to relate it to donuts. Regular donut, jelly donut, and donut hole in terms of what's happening there with our cells. Here's just a kind of a flow chart of some of those things that we've talked about. And in case you're reviewing this, we don't talk about any of this stuff, so don't worry about it. I'm not sure it's actually in your book. The slide's not from your book, but we did talk about everything else that's on here. Lastly, here in terms of solutions is dialysis. Dialysis is a process that's similar to osmosis. A lot of times when we do dialysis, for example, as in the laboratory in an experiment, we'll oftentimes use a dialysis bag, which might be sort of the experiment you'll see today, maybe, or this week. But basically a dialysis bag is kind of the same idea as a membrane. The dialysis bag, again, sort of, even though when you look at it, you can't really see it, but it's got like sort of holes or pores, if you will. Again, really allowing certain size molecules to sort of go through and filter through. Other ones obviously get stuck within the bag and it retains those larger molecules. In fact, this is very similar to, I think, the experiment for this week, which is you kind of put a whole bunch of stuff into a dialysis bag, you leave it in the solution, and every so often you would test the solution to see what managed to get out of the bag. And then I think at the very end, you crack the bag open and see what's still inside of the dialysis bag. And again, for example, in our body, right, kidneys do some dialysis and that type of stuff, right? So it kind of filters out sort of waste products and those type of things that we don't want. And then obviously, if that doesn't work well for you or for somebody, you know, they need sort of dialysis to help that process sort of be done for a person if their body can't necessarily do that. So we have very much sort of processes in our body where, you know, certain things are sort of filtered out using sort of membranes and stuff like that as sort of a way to sort of separate out things perhaps our body doesn't need and maybe retain certain things that our body does need. So that, again, dialysis is a very common sort of process, also very common in just sort of regular chemistry type experiments. Sometimes we want things in a certain pH, maybe we want it in a certain environment. For example, like proteins or something like that, I could put it in a dialysis bag, sort of put it into a solution, let it sort of sit there, and it will equilibrate maybe to the same pH as in the body, maybe the same sort of environment as in the body, and then you could kind of do your experiment sort of very similar to like it would be done, for example, in your body. Any questions on that there? That should wrap chapter 7 here, I think. Yes, it does. All right. Any questions on chapter 7 there? So we will just kind of get started on a little bit about chapter 9. Chapter 7, actually, since we're getting to the end, we'll just talk about a couple of things instead. So chapter 7 is the last chapter that will be on our next exam, which should be exam 2, I believe. And exam 2 is currently scheduled for 1 week from, I believe, Wednesday, if I'm not mistaken. And that should be that should be on, just to make sure here. Let's see, that should be, I believe that should be chapter 5, 6, and 7, if I'm not mistaken. So that should be what the exam's on. Let me just take a look at the schedule real quick here, just to make sure. Let's see here. This is the week of the 12th. Yes. So it should be on 5, 6, and 7. 5 is our chemical reactions, our, I believe, equilibrium, and our moles and stoichiometry and all that stuff. Chapter 6, which should be gases, all the gas laws, and chapter 7, which is our solutions, concentrations, molarities, and stuff like that. So that is when the exam should be. And I think since we just finished chapter 7 today, that gives you over a week. So I think for as of now, I think we're going to keep it on that Wednesday, which again should be the 21st of October. So we will take the exam on that. Also a reminder, because we are having an exam coming up, as we mentioned last week, we are having a quiz this Wednesday on chapter 6, which is the gases. So the plan is kind of like maybe what we did before. We will lecture at the start of lecture here for just a little bit. We will stop early, and then the quiz will open up and you could take it. And again, it will be on chapter 6, all the gas laws and stuff like that, which hopefully will get you studying and all that good stuff, right, for the exam that is coming up. That will then take us to... It is chapter 8, I believe. And chapter 8 is where we're going to go on Wednesday. I think I might have made a mistake and put chapter 9 up there, up online. But it is chapter 8. It's just labeled chapter 9. I'll change it in a bit here. But it actually is, I think, chapter 8 in this book. And that is acid and bases. So that's going to be our last chapter of actual sort of math and calculations is chapter 8. And then after that, we will skip chapter 9, which I believe is nuclear chemistry. And then we will roll right into chapter 10, which is organic. So we're getting to the point of the class where we got one more chapter to go, which is chapter 8. And that will be kind of it for calculations for a bit. And for the rest of the semester, chapter 10 and on, which is organic, there really is going to be kind of no calculations, no need for a calculator. More memorization and naming and that type of stuff. So again, as we talked about at the beginning of the class, we're rolling pretty close now into that sort of second half, if you will, in terms of, not a lot of calculations, more memorization, that type of stuff. So that's what's coming up, I think. Any questions on any of that stuff? So again, this Wednesday, we will lecture like normal. We will stop early. And then for the rest of the lecture period, before perhaps you have lab or discussion, you can go take the quiz and then obviously go off to lab or discussion, depending on which one you have on that day. And then a week from Wednesday should be the exam again over chapters 5, 6, and 7. And I think that's about it in terms of that stuff. Any questions on any of that stuff that's happening? Okay, so if you didn't put here, and we'll just stop there. No sense starting just to stop in a minute anyways. Have a good rest of your night if you're off to lab. If you have discussion, we'll start discussion around 7-ish, like normal. And you can go catch up on the Dodgers, see how they're doing. All right, I'll see everybody in a little bit here.